Today's web seminar is entitled How to Design Your Next Generation Filter Media Digitally. We will first import and segment the microcity images of this sample. We will then run a virtual air permeability test and determine the filter efficiency of this material. Then we will have a look on how to change the filter media design and give an outlook on how to predict the filter lifetime. Hello, and welcome to our web seminar, How to Design Your Next Generation Filter Media Digitally. My name is Jürgen Becker, and I am the head of Master Market Support Team. I was part of the founding team, so I have been with Master Market since the start of the company. Before that, I was a research assistant at the Fraunhofer Institute of Applied Mathematics here in Kaiserslautern, which I joined after finishing my studies of mathematics. Today's web seminar is entitled How to Design Your Next Generation Filter Media Digitally. So why would one want to do that? Why do it virtually and not directly create a real material? And the answer is that you want to save time and costs. It may take weeks to months to produce prototypes and run all necessary tests. Also, that may require more than one person or even different departments in your company to work together. Virtually, you can do this much faster. It just requires one person and one software, and you can do all the prototype production and all the tests. You may even go to the cloud and do hundreds of prototypes and tests at the same time. And only if your simulation says, hey, this new design will improve our filter, then you go to the prototype production and test it. Of course, you always have to do the test in the end, but you want to test it and find out that the new design works better. And by doing simulations first, you are improving your chances dramatically for a successful test. In filtration, we have to consider different length scales. If you have a filter positioned somewhere in a classroom, the aerosols need to get to the filter at all for the filter to take an effect. If you look at the filter, you have tubes and housing. And if you go down in scale, you can have a look at the element or just at a single pleat of the element. And finally, you end up with the filter media, which is the scale where the particles are captured and which decides eventually on the efficiency of the filter. And this is the scale that we will consider today in this seminar. In the web seminar, we will demonstrate the workflow on a sample material. The sample material is an air filter with polypropylene fibers of 15 to 20 micrometers. It's an electret filter and the charge is applied by corona charging. The product sheet shows that the basis weight is about 130 grams. We have a thickness of a little bit more than 1 millimeter and an air permeability of 1.3 meters per second measured at 200 pascals. We have made microcity images of the material sample, and we will use one of these images in today's web seminar. Furthermore, our partner in this project, the IUTA Institute in Duisburg, has measured the filtration efficiency of this filter material. The measurement was done after a complete discharge of the media with isopropanol vapor. And as particles was used potassium chloride, which has particle diameters below 1 micrometer, to test the efficiency at the most penetrating particle size. Measurements were done at a flow velocity of 20 centimeters per second. So today's agenda is that we will first import and segment the microcity images of this sample. We will then run a virtual air permeability test and determine the filter efficiency of this material. Then we will have a look on how to change the filter media design and give an outlook on how to predict the filter lifetime. If you have questions during the presentation, you can always ask them in the chat. There are 2 colleagues online that can directly answer your questions in the chat. Or I will answer them in the questions and answers session at the end of this web seminar. So let's switch to the live demonstration. So you can see here the graphical user interface of GeoDict, which is actually running on my laptop. So through the main menu, you can access the different modules of GeoDict. To load microCT data, which is the first step that we want to do, you have to go to the import menu. For microCT data, you choose import geo volume. The module appears here on the left, and we can browse to the files. We have them on our hard drive, and we select one of the many slices. Click on Open. Dialog opens that lets us crop certain areas of the image or determine how many of these slices we want to import. For the seminar, we want to import all the data that we have, and we have to set the voxel length because this is not stored inside of the PNG file, but you get these voxel lengths typically from the provider of the microCT image. And in this case, it's already written in the file name. So we enter the 1.5 micrometers voxel length here and continue with the image processing. So the image processing dialog opens. It shows 2D cross sections in the different space directions, X, Y, and Z. You can slice through the layers in plane, through plane view direction. And you can see, if you move here, you can always see where in the material you are regarding to the other directions. You have a histogram here of the gray value distribution over the whole 3D dataset. In this dialog, you can process and segment the gray value image. You have the option here on the left to change the image size. You can change the orientation and the alignment of the image. You can do gray value adjustments, and you can run all classical image filters to remove noise that might be in the microCT image, like a non-local means filter, median, mean, or Gaussian filters. There are also some special filters available to remove noise in FIB-SEM or microCT images. In our case here, images have a high quality and we don't need to run any additional filters. So we can directly go on and segment the image, meaning that we distinguish between solid, fibers, and background. So we go to the Image Segmentation and Labeling tab. And the simplest segmentation method is the global thresholding. So if we click here, we activate the segmentation overlay, meaning that we have this slider here that will show us how the gray value image is transformed into a here red and white image, where this denotes the fibers and this is the pores. So the methods that we choose is a single threshold that decides that every gray value on this side is fibrous material and every gray value on this side is pore. There are different methods available. We can choose some automatic threshold, OTSO and k-means, or a manual threshold. For the manual threshold, we can move the slider here and see how this would change the thresholding. And we see if we go too far to the right, the fibers dissolve. And if we go too far to the left, we see some artifacts appearing here, where some noise in the pore space is also segmented as a solid. And to get some good idea where we should choose our tracer, we can take the grammage into account. For that, we have to enter the grammage of polypropylene, which we can look up to be 910 kilograms per cubic meter. And the grammage plane here is the XZ plane because the Y direction is the through plane direction. So we can see here what the effect would be on the grammage too. So, and if we take into account that the grammage should be somewhere where we would expect it, and the data sheet showed it was between 110 and 150. And if we look here in the different slices, we see that 20 is quite a good number where we don't see any artifacts and we have the fibers segmented nicely. So yeah, we select this threshold and the grammage is in the range where we would expect it. So we can directly create a segmentation here. And close this dialog. So now in GeoDict, we have the segmented structure and the gray values still there. So we can remove the gray value image and switch to 3D to get a better view of the structure. We can turn on some effects here that give a better view on the depths of the 3D visualization. So we have now our filter media from the CT image imported into GeoDict. But before we start to run computations on this, we have to do some post-processing still. So first, we cannot be absolutely sure that there is no noise in the media, and there might be some small artifacts, maybe like this, but they can also be in the center of a pore where some noise has been segmented as solids. And this has a big influence on the computed results. Imagine that you have in the center of the pore some noise pixel that has been turned into a solid material, and you compute flow or stimulate the movement of particles through the pore. All the particles will be captured at this single grid cell that has falsely been turned into a solid material. So we have to make sure that we remove them. And we can do that with Process Geo. There's an option that is called Clean Structure. In the clean structure, we can say that we want to cleanse the solid and that we want to turn all parts of the material that are smaller as a threshold into pore space. We can directly turn that into pore space, but if we want to see what is happening, we can make an intermediate step and turn this into this green material here to see what we have, marked. And we can set some small number like 500 or 1000 here. And remember, we are in 3D, so 500 really is a small number. It's just 10 by 10 by 5 grid cells. So this is really just a very small part of the structure. And we can click this here, click on cleans, and then we'll see in green some of these small parts here. And if we actually set the material to be invisible, we can see that we have some of these green points also somewhere in the middle. And yeah, these are really the things that should be removed before we move on and compute any flow. So in a second step now, we want to remove the green ones, and we can simply do that with reassigning the material from green to pore, and then the green parts here are gone, and they remove also from the visualization once I move it. So there's now one additional point that we need to do before we start the computation. In FilterDict, the flow is always computed in the Z direction. So particles will always move from here to there. And we see that's from here to there. It's not the right direction for this microcity image. We would need to compute it from here to there. So we have to turn it around. And we can also easily do that by rotating 90 degrees around the x-axis. And then we have the sample in the right direction. And if the flow goes in the direction of this arrow, it goes through the filter material like we would want to do this. So we have now our structure ready. So we simply save it intermediately to have it available later on. Filter structure, or given any other name, and have this stored. So what is the first thing we want to simulate after we have finished with import and segmentation of the CT data? Well, the next step is to compute the air permeability test. For this, we have to change to the FlowDict module. We can find this under the prediction modules. One has to know about the air permeability measurement, that the flow is measured at a pressure drop of 125 or 200 pascals. In both cases, this results in a pretty fast airflow. So we are no longer in the linear Darcy regime. And that means that we cannot simply rescale the resulting flow rate from 125 to 200 Pascal. And it also means that we have to solve the nonlinear Navier-Stokes equations to get these results. And we can either do this in FlowDict with the Navier-Stokes-Brigman command, or we can use a specialized app that is also provided with FlowDict. And we can find this here under the Flow apps. So we have here two choices for air permeability test. One is the direct method that directly computes at the given pressure drop the flow through the material. And it might happen that at 200 Pascal pressure drop, the flow already becomes turbulent. In these cases, you can't compute a stationary flow directly, but you can still approximate using the Forsheimer approximation, which is the second app. In our case, we can still compute stationary flow, so we can use the direct method. And you see, if we click on the edit buttons for the options, there are just very, very few options. So the only thing actually that we have to give here is the pressure drop and a name of the result file. We have a selection between two flow solvers, but the default LER is usually the better choice, so we can just use it. So we just click OK and could start the computation with clicking on Run. This takes a little bit too long to present live, so I have pre-computed this, and I will just load the result. So I go to the pre-computed results and load the test result. And you can see here is the green dot that this belongs to the structure that we have here. And is this here? You see that this is the air permeability computed at 200 pascals. So, and if we remember what was written on the product sheet, we had an air permeability of 1.3 meters per second. And the computational result is 1.32 meters per second. So it fits very well to the expectations. So as a next step, we want to determine the filter efficiency of this sample. So what is the concept behind the efficiency simulation? Again, we will take our filter model, and then GeoDict will compute the flow through the media, as we have done for the virtual air permeability test. But now Additionally, GeoDict will track the movement of particles through the filter media. Some of the particles will pass the filters and some not. And this will give us the initial filtration efficiency. And for the initial efficiency, we can already stop here. Additional steps 4 to 6, we only need later when we consider the filter lifetime. So let's get back to the live demonstration. So we close the results, and for the filter efficiency computations, we open the module FilterDict. In FilterDict, we can select the scale first. So here we are on the media scale, so we choose filter media. For filter media, we have the choice between two different commands, either filter efficiency or filter lifetime. We'll start now with filter efficiency and click on the options. So the filter efficiency options open and they are organized under multiple tabs. On the first tab, we have to set the filter experiments and especially the mean velocity. So the measurement was done at a flow rate of 20 centimeters per second. So we enter this here. We can keep everything else on the default values, but let's have a look on them. So as I said, the flow direction is fixed, the Z direction. And the flow motion, we have the choice between slow, creeping flows or fast flows, where we have to compute the Navier-Stokes equation. So the velocity here is much slower than for the air perm test. So in our case, it's still possible to use the Stokes equation and the slow flow here. In general, if you're unsure, always select the fast flow. This will always give the correct result. Fast flow will also give correct result for slow flows. It just takes longer to compute. And you can speed things up if you know initially that this flow is slow enough. Here, you can set the boundary conditions for the flow and for the particle movement. For example, for the boundary in tangential direction, you can select if particles that leave the domain on one side enter on the opposite side, or if you choose symmetric, bounce back at the boundary. You also can select between slip flow and no slip flow at the fiber surface, but for fibers of diameter 15 to 20 micrometers, no slip is the right boundary condition. On the next tab, the constituent material tab, we have to select the materials. So first the fluid, we simply set to air, and the solid, we take polypropylene, and that's it on this tab. On the particles tab, we have a number of sub-tabs. So first, positioning, we have to set the initial particles. We can keep all the defaults here, meaning that we create particles on the inflow plane with some offset to the plane. They are distributed uniformly. We take 1,000 particles per type, and type will later be the different particle diameters. And of course, the positioning has some random seed. On the movement tab, we have to select Brownian motion and the Cunningham correction to correct the diffusion of small particles. Cunningham lambda here, the default value is the mean free path of air at ambient conditions, so that should fit here well. On the electrostatic effect tab, well, remember that the measurement was done after discharging the media, so we don't have to include electrostatic effects. On the interaction model tab, we now have to select the collision model. Collision model means to decide if particles that collide with a fiber, stick to the fiber, or bounce off. Here we select cordon first touch because we assume that the small salt aerosols that we have used in the experiment will not bounce off. For the density, we have to set the right density here. And for the potassium chloride that was used, we can look it up, and it's 1,980 kilograms per cubic meter. Again, here we have to select Brownian motion. Now, last but not least, on the size distribution tab, we have to give the particle size distribution. So typically, you will get that from some Excel sheet. So you can directly import from an Excel sheet. So you clear everything here, open your Excel sheet with the diameter distribution, and then just Control copy, click in, no, click in the control. So the only thing you have to make sure when you copy is that the percentage is given. If it's count percentage, you select count here. And if it's mass percentage, you select mass. And if it's volume percentage, you select volume. And don't mix up the percentages, because then the distribution will be very different. So here we had count percentage, and here's the particle size distribution. Yeah, you see it ends at 1 micrometer here, so it matches the size distribution from the experiment. Yeah, these were the particle tabs. Now on the solver tab, you can choose the parallelization. Usually it's select automatic. And yeah, for most cases, you can leave all the solver parameters as default. And there's a number of advanced options if for some reason the flow solver runs into trouble. There are some possibilities, but usually you don't have to do any changes here. On the output tab, you can decide which files are written on the hard disk. So the default is to keep all the files. If you know exactly what you need, you can switch off some of the files here to save some space on your hard drive and in runtime too. And the last tab only contains some formulas and references, nothing to set here. So we click OK here, and then we can let it run. It takes only 10 minutes to solve here on the laptop, but that's still a little bit too long for the live demo. So I open the result too from the pre-computed result. Yeah, and you can see here the runtime was just 470 seconds. And you see here the list of results. I enlarged this a little bit. So we have the list of all the particle diameters, and for each of the diameters, the efficiency. We had simulated 1,000 particles for each of the diameters, and this gives a report of how many of them were deposited and how many of them on the outflow, which then can be plotted and gives this efficiency chart of diameter to efficiency. Yeah, and how does this compare to the measurement? Here's the chart. So we see again here the 3 measurements, the average from the 3 measurements, and the simulation that fits very well to the measurements. And for some reason, it fits very well to this light green measurement. Okay, but that may be random. What have we done so far? We have imported a microcity image of an existing filter media and reproduced measured results. So What comes next if we want to design the next generation filter media virtually? Well, we have to move from an image-based 3D structure to a model-based 3D structure, which we will be able to change. So if we just compute results on microcity images, we can only compute results for already existing materials. So we have to go to non-existing materials to try new designs, meaning that we can't use images, but we have to use models to compute the results. To find the necessary input parameters for the models, we can first analyze the existing material further. GeoDict offers many options for this. So, for example, you can use fiber find to find fiber diameters of the material. And it reports the average found material and the standard deviation, and you see a distribution. You can use MudDict to analyze thickness and inner porosity. So you can see here the density distribution in the through plane direction and some estimated thickness. That would be 890 micrometers here from here to there. And what's the solid volume percentage inside of this media. And last but not least, you can identify individual fibers and analyze the fiber orientation with fiber find AI. And this will result in an orientation tensor that tells you how fibers' directions are oriented. So now let's see how we can use all this gathered information to design a virtual material. And the first step is that we want to create something that looks like the real material, so that we have a good starting point to add modifications on it. So we start with something that looks like the real material, and then we go from there and modify it. So going back to GeoDict. So the module to create models is FiberGeo. And in FiberGeo, we can use the create fibers command for this. So let's have a look at the options. So first we have to set the model size here. And we select something that corresponds to the image that we had. So we choose 500 in X and Y direction and the same voxel length to get something like the same size. And here we choose the thickness. So we set this 596, which results in the thickness that was measured with MudDict. Same, we have to decide how many fibers are added to the model. So we have to set the solid volume percentage that we want to reach, or you call it the grammage or the porosity. That's what we set here. And on this side, we have to decide if these fibers in the model are allowed to overlap. So for the first try, we allow them to overlap because that's the simplest and quickest options. But we will change that in later steps. So on the second tab here, we have to define the fiber type. So there was just one type in this media, so we removed the second one. And as a first assumption, we assume that the fibers are straight and infinite in the sense that they are longer than the cutout that we are looking at. So we set the material here again to the one that we want to use, 100% of this type. Then we have to set the fiber diameter, and we can set it to the found Gaussian distribution. So we take the values and define some distribution widths that cuts off. And for the orientation, we can also enter the values that we have found in the analysis. We select orientation tensor, and then I have to look what the values were. I was 0.5971, 0.3873, and 0.0155. Normalize that. And can just compute it. So this is the first try. We click OK and generate. The result window. So we have here now a 3D model with fibers of the same size and same orientation as the real material. We can still see two differences. So A, the fibers are too straight. In the real material, they have some bends and slight curliness, and the fibers intersect with each other. Yeah, and we can fix this. So first, let's use some curved fibers instead of the straight ones. So we leave everything here on the first tab, but instead of the infinite circular, we choose another fiber type. So we can take the curved circular. So we add this and remove this one. Choose the material again. Then we set the same parameters here. So we have to set the diameter again. Same numbers as before. We now have a length, and we choose some length that is longer than the domain, so that the fiber will still go through the whole domain. And again, set the orientation as before. So I still enter the numbers again. And okay, so we have the same diameter, orientation. Now we have some additional parameters describing the curliness of the fibers. So for the random curl, the fibers change the direction after each segment length. And these parameters below here describe how the direction of a segment depends on the direction of the previous segment. The local straightness decides if the fiber keeps the direction or the curvature from one segment to another. And the global straightness decides if the fibers tend towards the main direction or not. So we can put 1/2 in here as a first try. And let's see how this looks like. We close this dialog. And now we see that we have fibers that are not so straight anymore, but still straight enough. And it looks a lot more like the real material. So they still have one mistake here, that the fibers may intersect with each other, which of course in the real material they don't do. But there's also a solution for this. We can switch off this allow fiber overlap and instead choose remove fiber overlap. There's then an additional dialog that lets us select how GeoDict may do this. You can mostly keep the defaults, especially that here you can decide to allow a little bit of intersection. But yeah, that's up to you. Of course, this also takes a few minutes to compute, so I'll just show how the structure would look like if we do it like this. Yeah, so we have curved fibers here, and now the intersections removed between them. So, where are we now? We have now a model of a filter media that is very close to the real material, and we can now start to apply changes. For example, we could add a second fiber type. We can choose smaller fiber diameters, thinner medias. You can add additional binder, higher porosity. We can add 2 layers. Yeah, so there's an infinite amount of possibilities that you can check and try. And of course, the advantage of doing these modifications digitally first is that you can create them at almost no cost. You don't have to create any prototypes or do tests. You just need a few clicks on the computer and have all these virtual prototypes available. So now, very briefly, a short lookout on filter lifetime. So simulate filter lifetime, we can start exactly as for the filter efficiency, the first 3 steps. So we have the model, GeoDict computes the flow and tracks the particles. But this is just the initial set of particles. Now the captured particles, they are added to the filter structure because they will block certain flow paths. So what we have to do after some of the paths are blocked, we have to recompute the flow. And then a second batch of particles is tracked and so on and on. So over time, more and more particles deposit on the filter and the pressure drop increases. And that will then let us simulate how a filter cake builds up. In this case, particles come from the right-hand side and move through the filter or are deposited on it. And here we have selected another test dust. So this is one of the standard test dusts, not the small particles that were used for the measurements with the potassium chloride, where the largest particles were about 1 micron. You can see here that the particles are a lot bigger in that case. So like this is usually done for the lifetime tests. Yeah, and with this, I already come to the questions and answers. Want to ask if you have some questions. Yeah, I see one published question here asking if these measurements are the results from filter efficiency simulations, measurement 1, 2, 3. The measurements are not the result of simulations. No, they are the result of measurements at a test bench at the IUTA in Duisburg. So there was the real material sample and they did a filter efficiency measurement. We took the same sample material then, made a microcity image of it. And this was exactly the image that we just imported in GeoDict, and then we ran the simulation on this image. Yeah, there's another question for the dust holding capacity. Is there any simulation done of the dissipation of the electrostatic charge? Not in what I have presented today. This is also not directly included in GeoDict, but we are working on this in a project with the IUTA, and there's the possibility to set the electric charge on the fibers and on the particles for the filter efficiency simulations. There's also a simple decay model implemented in GeoDict that you can use, where you can relate decay of the electric charge to either the amount of dust deposited or time in the experiment. But this is a global decay, not a local decay regarding the deposition of particle at certain places. But yeah, in that sense, you can model a few things in that direction. Yeah. Next question is, how long does it take to create the images needed for input into GeoDict? I suppose this is with question to the microcity images. So Yeah, I mean, doing a micro-CT image is a little bit of an effort, I would say. So, I mean, you need the micro-CT to do that. I mean, or you have to send it to a service provider. So we don't have a micro-CT ourselves. We send it to a partner that creates the images for us, but it's not absolutely necessary to have them. I mean, you can of course do all the modeling and create models without having a micro-CT images, but it makes of course sense if you want to analyze an existing materials as a starting point for your simulations to get one or two of these images first. But you can just send a sample of these materials to a partner and you get the image a week later. And it costs something like 700 to 1,000 euros per image. And one other question about the correlation of Cunningham setting and particle size. What is the reason only use one kind of Cunningham coefficients in multi-particle size during simulation? Well, as far as I understood, Cunningham correction coefficient, this is a formula where the mean free path enters, and it's valid for all particle diameters. So I mean, the formula is implemented in GeoDict, and the single parameter this goes into is this lambda, this mean free path, and this gives the Cunningham correction for all particle sizes. I mean, the factor is then computed for all the particle sizes. But this is also available as user-defined functions. So in principle, you can change it and could implement any kind of correction. Have you published a study showing the accuracy of the simulation and the correlation to real filters? Yes, I mean, there's a number of papers, mostly from our customers, where for different examples this has been published, and maybe Philip can add that in the chat, or you ask later to support, and you can get some of the papers. Next question is, what is the effect of varying voxel lengths on efficiency simulations in terms of accurate results? You need to have a sufficient accuracy in on the fiber size. So, I mean, fibers need to be resolved well enough. At least a fiber diameter should be 10 grid cells to have accurate results. And if you go down and the resolution is too coarse, then typically what happens is that the simulated efficiency goes up. So the simulation will tell you that you have a higher efficiency than you have in reality. Yeah, you need to have sufficient accuracy on the simulations, but you don't need it for the, as you see here, we had in the example, we had a voxel length for the structure of 1.5 micrometers. So this is one grid cell, and we have just considered particles lower than 1 micrometer. Yeah, so you get the good numbers also for the very small particles, even if they are much smaller than 1 grid cell. But you need to have the flow around the fibers resolved. What's the effect of different sample size on efficiency simulations? Yeah, of course, you have to take care that your sample is large enough to be representative. And you also have to take care that, I mean, if you look at the real material, you should always maybe take more than one micro-CT image, maybe 2 or 3, and have maybe one with a larger field of view to get an impression if there are some variations on the material, and that if you take a cutout and do a simulation, that this is representative of the complete material. If the filter has some holes somewhere where you don't look, then this will of course influence the efficiency a lot. So yeah, you need to to think about what is a representative part, and there's no general answer for all the materials because it really depends on what type of material you're looking at and what the length scales are in that material. It's the same for efficiency or lifetime. So in general, I would recommend to have it a little bit larger than the one that we are just doing in this demo to make sure that you have a representative area. But here it worked well also for that size. The next question, will a rough surface fiber be detected in GeoDict? Do you resolve matching on rough fibers? I actually don't know. So that would depend a little bit on what do you mean with a rough surface. I think I would need to see how this looks and what effect that would be. Yeah, and here's one more interesting question. Can you apply your models to activated carbon blocks? We also have the module Grain Geo, where you can model grains. And on the last user meeting, there was a presentation where we created a model that combined fibers and activated carbon in one combined filter. And I think that is also available on YouTube. Yeah, today we looked on the filter media, and I just want to mention that there will be another web seminar coming up in September. The exact date is not fixed yet. That will have the simulation of the complete filter as topic. So we will there be then on the centimeter scale and look at structure like this, where we have the flow in the casing and filter modeled. But before the seminar on the complete filter will be this, the next web seminar will have the topic, what is a pore? Understanding porosity and transport in porous material. And this will take place on July the 1st in the morning. So the topics will be some explanation of what are pores, how they are measured with GeoDict, and there will be some examples on batteries and rock structures. And with this, I thank you for your attention. And as I said, if you have some additional questions, feel free to write an email to support@mass2market. You can, of course, also access our forum and ask questions there. Or you can have a look at the user guide. It's also online, and you can get some information about what GeoDict can do there. And with this, I want to thank you and wish everybody a nice evening or nice day and say goodbye.